Today, I would like to talk about concept-based design, and this is I will describe what it is. So, if you happen to have the angle brackets in your code and you have some templates, it's not easy to design such a library that have a lot of templates, because the compiler error messages are cryptic, and you can do a lot of you can do a lot of bad decision, and it's very easy to come up with something unreadable and unusable if you are doing C++ metaprogramming. That's why it's extremely useful to use best practices in that area. So what we will do what we will do in this talk, we will try to design a simple library that is not that simple, but it's simplified version of the standard ranges. And we will go through the design decisions, and we will see how it looks like in real, the designing of such libraries. So we will limit ourselves to input streams of data. So we let's assume that our data can be consumed in the form of such interface. I'm calling it cursor. We have a get method that returns the value as a const reference. And we can iterate in one direction. We can query the next value with the next method, and we can query if it's the end of the stream or not with the done method. That's it. So pretty simple. And this will model our concept. So this will be our concept, and this particular sum cursor will model the concept of cursors. And we are going to have a couple or two template functions that will use this interface. And so using this interface means that we will instantiate with that our templates with that interface, and we will use exactly those methods of the cursor and not others. So here is the example of the usage. It requires I forgot to mention that here, even though you don't see angle brackets, this is a template, and this is so-called abbreviated template, the new feature of the C++20. And the idea is if you have template without any requirements, you just replace the name of the variable with auto, and it works exactly like if we will write template class T and replace auto with T. Okay, so in this method, we just want to dump our data. So we iterate using this next and done methods, and we output the data to stdout. So the cursor is passed to the method by value. It's not a typo, and it's by design. That why? Because it will be confusing if we will pass it. So we cannot pass it by const reference, obviously, because we should iterate the cursor, and this next method is not constant. Non-const reference will be confusing because we want to dump. It's an operation that we assume because it changes the value to cursor. The cursor after the dumping goes to the done state, yes, and so this means that it doesn't make sense to pass the reference, because after the operation the cursor is not usable anyway. So we can either use double reference the temporary object, or by value. But by value is more general, because if we pass by value, you can use this function with temporary, or with or otherwise the function will copy your cursor. So let's formalize our requirements with the C++20 concepts. It's just an example how it can be done. So first we define the cursor, the concept of cursor, and I'm not going to go into details of the syntax, but it is important that we what we are going to say in this concept definition. We just enumerate the requirements that we have for the cursor instances. So we want this cursor to be at least movable. So we want to have move constructor for this cursor. Otherwise, for example, this dump function will not work. We should have this cursor either movable or copyable. And we additionally require that that if we have some object of type T, in this case cursor, it has done method, and the result is convertible to bool, and it has get method, and the result is const reference. So to achieve this requirement, we need to add additional secondary concept is reference that is trivial. So we use standard is L value reference and is const for that. And we also want our cursor to have next method. So for the cursor definition, we can add additional assertion that specify that it's really models the cursor.
Anton, there is a question. is, can you please repeat why we shouldn't use a simple reference?
I see. It doesn't make much sense to use simple reference here in the dump definition, because after dump is executed, we cannot do we cannot use this cursor. It is you see, the condition is for this for loop is that cursor is not done. So after we exit the loop, it is done, and we cannot get any values from that. So it's well, it's useless, and well, it's better to have it's better to not not so it doesn't make sense to pass the reference to the dump and then use this cursor in any other context. Okay. So let's continue with those C++20 concepts. So and the concept itself, it can be used in two cases. Firstly, it serves as a template variable of the type bool, so we can assert on that. For example, here we assert that some cursor is really modulus a cursor, and also we can restrict the declarations of templates with that cursor. So here we add. So you see the difference in the first slide. We have auto car, and now we have cursor auto car. So this means that this function will only be, this template can be only instantiated with the class that requires cursor requirement. And this is purely so, and what compiler will do after this, we add this cursor, it will, before instantiation of this dump, it will go and check all requirements for the type, and we will literally check that. So it will not attempt to go to the function body. So this means that error messages will be not, in the case we pass something, some garbage to this dump function, error messages will be different. For example, in this generic dump, we will have some errors that points inside the dump. And in case if we specify that it satisfies the cursor, the errors will be only about the declaration of this dump. So basically, compiler will say that there is no such a dump function, and the only candidates requires that we have the parameter that is cursor, and we are not. Okay. To let's ensure that we did something useful for this for this concept definition, and let's design something that is usable as a concept. Let's do the class that models an opened file. So we can just read the data from this open file once. So and it is pretty straightforward. So we use C standard library file interface that has file open, file close, and file get char, and the whole thing is just a wrapper against it. To manage the resources, namely the file pointer, we use unique pointer. So you see it has a custom deleter that will call fclose for us, and to keep the current value that we fetch from the file, we will use optional. If optional is almost the same as the value, but it has additional state where we don't have any. So and the state where we don't have any corresponds to the situation where the stream is over, and and we're done. So here we can see. And to get the value, we just get it from the optional. And next, we'll do the following. We will read the symbol from the stream, and we check against the end of file. And if it's end of file, we make the optional carry known. We can in principle we could write a std known here, but I like this notation. It also works, and it's more elegant for me. Otherwise, we just pass the character, and this works fine. Okay, let's take another model of this concept. In this, that's much simpler. Just we will present the sequence of the so we will present sequential numbers. And for that, we just keep the current number and we just increment it in the next method. Interesting fact that this sequence is infinite. So done just returns false, and we this reflects the lazy nature of our cursors. So we have finite class that represents something infinite. Yes. Well, if we will try to use this cursor as is with the dump method, we will fail, obviously, because it will be infinite cycle. What we want to do, but we want to test our stuff, so we probably want to have something that looks like take the first 10 elements, like that. Well, how to do that? Let's introduce another cursor take that will be a wrapper against the original one that is template parameter. Okay, we have template parameter and we want this template parameter to be a cursor. It's a good opportunity to use C++20 concepts. We, instead of class here or type name, we just write cursor, and that's it. So the implementation is quite trivial. So we the class contains countdown, and each time we do the next, we delegate this next to the the base cursor, and also we manage this counter, and if counter goes to 0, we're done. Okay, so it kind of works. So and this in this example. Okay, let's do some let's twist a little bit this take interface. Let's do the following. We rename this. By the way, this example will work even though take is the template, but we are not having angle brackets here. It's because it is because class template deduction that Mauro introduced 2 days ago. Let's now make a little twist. We rename this take to take car, and but take will have another definition. It will take only one parameter n, and it will return a functor that takes a cursor and returns another cursor. So, and in this this functor will transform original cursor to the take cursor. Okay, so what we just done, we have bound the n value in the value of the n to this lambda. You see this n in the capture list. Okay, so and to use that we have to add this extra extra parents. So now take 10 returns a function, and then it is applied to numbers from cursor. So why we are doing that? Because, well, it's if you think about that, we want to introduce another concept, the cursor algorithm, and we will treat any function that takes a cursor and returns a cursor as algorithm. For example, in this case, take is not algorithm, but take 10 or take 9. It's returns a cursor and takes a cursor and returns a cursor. And using the same scheme, we can produce quite a lot of useful things. For example, we can write algorithm that filters the values within the cursor or transforms those values to some others. Here is the examples of the interfaces, or we can do some more complicated things like moving average and whatever. By the way, I forgot to mention that I copied the link to those slides in the chat, and for each slide there is the link to the compiler explorer to the compiler explorer, so you can test all the examples on your own. Okay, and in these examples, by the way, I have this filter implemented already. Okay, So what why we are doing that? Because the functions that are written in this way, they are composable, and we can easily compose some decompose some complex algorithms to their parts. For example, say we have some algorithms that have parameters, yes, and we just want to, so it's an algorithm, it takes the cursor and returns a cursor, so it's as clear in the definition, and we want to first filter our input data. We take parameters from the first arguments. We do that. We take some first first elements in the string. We do this, and we filter again, and we do some other stuff. So this is the way how we can decompose our algorithm into the parts, and this is important. But okay, there is some readability problem though. We have a lot of parents in at the end, like in Lisp. Well, and we probably don't like that. But we can notice that this is actually just a composition of the function in mathematical sense. Let's add let's express it as a function. So our algorithm literally is composition of other algorithms, and now it looks much nicer and more readable. The problem is that we should implement this compose function. Turns out it not a big deal. So here is the full definition of that. So we have if we have one function, we just forward this. We just return that. Yes, we used std forward, and this is the example of perfect forwarding. Yes, so we use universal universal reference here, and if it's if f is temporary object, it will return temporary object, and if it's some L value reference, it will return L value reference as well. Okay, so and the rest of the compose is defined recursively. So if you have some functions and others, we first compose all others into some function that is called G. And then we move F and J into the capture, and we return another functor that takes its arguments and perfect forward it to the composition of F and G. Easy. So, but what if we want to do like std ranges does? We want fancy pipe syntax. So that instead of writing dump take numbers with all those parents, we just want to have this fancy notation. No problem, we can do that, and this is what we want. This is here. This is the plan how we want to implement it in C++. Yes. So if what pipe operator should do. So if f from x is valid expression, we want to evaluate it just for f and x, and otherwise we want to do function composition. Well, here is the implementation of our plan. So the code is polluted with the std4 with the perfect forward with perfect forwarding stuff, but we can see that we just query if if G is invocable with F. This is the first case, yes, and we return that, and if not, we return function composition. So here is the interesting thing is this if const expr construct. Here, if const expr serves as a single word, I would say, and it's not the plain if, and it's only works if the expression here can be executed in compile time, and note that return value in two branches of this if is different. And in fact, it will be only one return value depending on the parameters. And what this function actually does, so what compiler does with this function, it creates two functions. One will be with while one will two overload functions. One will be called if the condition is met, and another will be called if condition is not met. So we can do the same with this std using Sphinaya with std enabler, but this obviously looks much nicer. Okay, so we now try to use our dump, our fancy pipes like in the desired form, and we will fail in compilation. Why? Because this dump is not an object. As you may know, in C++, functions are object, and they can be passed to the functions, but not templates of the functions. And this is this dump is uninstantiated template, and it can be it can be passed to the function. So we are failing here. But luckily, there is an easy way to fix that. Instead of having this template, even though it's in abbreviated form, we will have the const expr inline variable, global variable that that is instantiated with the lambda of the same body, and this will make and by the way, this lambda is also it's a generic lambda. It takes all cursors, and well, and this will make the trick. So now this work, but the outcome is very important. Maybe that template functions are not the first citizens, and the functors are better. And the only nuance that you already know about is that such variables, they don't participate in in ideal lookup, and that's why they are called nibloids. Yes, and but we don't care in this case, because we probably will don't want to use this dump with anything except Karster. Okay, so another challenge that we can have. Suppose we have a huge library that do language translation, and we want our interface of our library to be expressed with Karster. We can do that in that in that style. So we have this translate function, we pass from and to languages to operate with, and this function will return another function that take a cursor and returns a cursor. But well, and we will have this implementation here. But there are some problems with that. And for example, the implementation is quite huge because, well, we are using some advanced techniques to do actual translation. But the problem is that with this inline, in order to have this function to pass to provide this function to the user, we should instantiate this guy, because this is a template author, you see, on the user side, and this will make will add to problems. So our header will be that will contain our functions will be extremely huge, and it will be exposed to the user, and all compilations error will be on the user side, and compilation time will be huge. So how can we fight without it? Apparently there is the standard method to deal with that situations. It is called type erasure. You already know what type erasure is. You already met one type erasure. It's called std function. And so if we pass something to std, some functor to std function, we will get the new type that doesn't that will be the same for all of all functors that are passed, all possible functors, so of the given signature. So you can pass anything to the std function, and the type of this and the type will obviously be the same. So it that's why it's called type erasure. It erases the actual type of the object. So we can do for the cursor. Let's introduce another a type that is called any cursor. It is instantiated only for the value what basically gets returns, and this class will act as type erasure. So we can combine function and any cursor to declare the type of what we want to create, and this is concrete type. So we can now the signature of our API function is transformed from auto to that, so it returns concrete type, and then it means that we can detach the definition and declaration of those functions. So this will be in our header, and the actual definition declaration will be in our header, and definition will be in our CPP file. And now we can compile it separately, and user will get only the header. So what how can we do the type erasure, and how it works? How it works? Apparently, for the simple things like cursor, we can fit type erasure definition in one slide, and here it is. Let's go into details how it works. So we have the constructor that is basically templated, and it takes any cursor, any. And what we do, we instantiate our implementation with the new impl. Okay, let's go and see what impl is. Impl is unique pointer of some interface, and this interface, so it repeats the structure of our cursor. So it has done, get, and the next method with the proper signatures. And and we hold the unique pointer of the interface. But when we instantiate this impl, we create not the interface, because it's even impossible. It has pure virtual functions, but we create the concrete instantiation, and this concrete instantiation is templated by the cursor, and it just delegates all of the methods from the cursor. So this means that if we pass the concrete cursor of type T to the constructor, so the concrete implementation of the interface knows about the type T, and we use it, but apparently the interface doesn't, and unique pointer that holds interface doesn't know about the concrete type, so the information is erased. And we use from the public method of the any cursor, we our done, get, and next methods are delegated, and but the only thing that that now we worry about is the destructor. And as for destructor, unique pointer will call interface destructor, and it is declared virtual. Virtual means that base class will call derived class destructor, so this guy, and destructor will work correctly. Okay, this is type erasure. So now let's assume that we have another challenge. Suppose we have developed quite a bit of our cursors, and suddenly we have found another library where the same approach was taken, and some other algorithms are implemented that we don't, and we want to use that. And the approach is the similar, except that the author uses first letters in capital for the method get, next, and done. So then obviously those classes that that in the other library, they don't work with other cursor, because it's not a cursor in our sense. So how can we fight that? Of course, we can write a simple wrapper that okay, so I think I did it wrong, but of course we can have a simple wrapper that that takes the another API input and just translate get with capitals with get without capitals. Here I have a typo with done. It should be with capital, and this will work. But it's quite annoying, because we want to prepend all API, all objects from other API with this wrapper, and it's well, we can do better. So what we can do? Let's return to our cursor template definition. Here it is, yes. And let's do it slightly differently. Where is it? Okay. Let's add additional namespace for our purposes, and we will do the following thing. We'll have a function cursor done that will return car.done, and additionally it will have this. So yes, I understand there are a lot of tautology here, but you will soon understand why it's needed. So we return, instead of having just auto, we return Jekyll type. We provide the type. We specify the type in that manner, and this enables sphenaire in our case. This means that if we will try to instantiate this cursor done, this is the template, the abbreviator for. If we want to instantiate this template with something that doesn't have method done, we will fail, and this failure will just so constant. It's not an error, because sphenaire stands for instantiation. Instantiation error is not a failure. And this compiler will not use this cursor done for the overload resolution. That's it. And here, for all others, is this we use the same trick. And okay, we define those cursor done method, and then we will write the nibloids for them, and those nibloids are also with this sphenaire enabler trick. And so nibloids delegates to cursor done, and cursor done delegates to car.done, and so on. And after that, and the cursor will refer to nibloids. So, and cursor concept will refer to nibloids. And obviously, this cursor concept reflects the user-facing contract, and this means that we, for all our functions, instead of using card.done, we are going to use those nibloids instead. So, what? Why all this tautology is needed? Okay, look what we are going to do now. We take this we just define for our problem in our problematic namespace three templates with the same name that we use here: cursor done, cursor get, and cursor next, with the proper implementation. And now suddenly our cursor becomes a cursor. This another cursor becomes a cursor in our sense. How it works? Let's track for the done. Okay, so here we are calling this nibloid. Nibloid is refers to cursor done, and now cursor done is a function, and that's why AGL argument dependent lookup is enabled, and we see that in our particular case the cursor is implemented in another API namespace. So first we are looking for the cursor done in this namespace, and we can find it. Here it is, and this will this exactly what we will use here. So the outcome is the following: if so to define the cursor method, we need to have this cursor done functions available by AGL lookup. But alternatively, we can skip defining them, and then we will use fallbacks. And these fallbacks will only be triggered if we don't have cursor done available by AGL. Yes, and those fallbacks will go to for our previous definition. They will delegate to the methods if the type does have them. But if it doesn't, well, then it's not a cursor. So, but now we can benefit from that, and we can even improve this mechanism even more. We can notice that some of the cursor method can have defaults like done. So we can, if someone wants to define the cursor but don't want to define the cursor done, probably he means that the cursor never done and it's infinite. So let's add additional method that takes eclipses, but this syntax is inherited from C, and it's not very popular in the C++, and that's why according to the C++ overload rules, this is the last thing what compiler will check during overload. So the the functions that takes eclipses, they are have the lowest priority, so we can safely use them as and to be sure that it will be only the last opportunities that compiler will check. So what it means that, for example, if we will do we will going to implement some alternative form of this number from cursor, we will do like that. We'll just implement friend function cursor get and friend function cursor next, and cursor done is already implemented in our case, and it's a cursor, even though this struct doesn't have any methods. Okay, so now we end up with quite rich definition of what can be treated as a cursor, and this is the interesting thing, because, well, it's quite flexible, and using this technique we can do something even more sophisticated. So for example, and it's and this is really used in practice. For example, you know that for the ranges, so many C array can be is treated as a range. STD constructor that has begin and end is treated as a range, and everything that has begin and end as available by ideal lookup will always also treated as. So this is the typical thing for the concept based design, that we have this ideal mechanism to enhance the notion of our concept. Okay, the next and it will be the last thing, the range loop. So at the end, dump is probably not the dump function that we had before is probably not the is probably not that flexible, and we want to for our cursors to have this to support this range for loop syntax like that, and this would be this would be more natural for them, right? And it turns out that it is not that hard. So, and if you will look up in the reference, you will notice what how range for loop is implemented. So compiler will, when it finds something like that, it transforms this literally to that snippet, where in yellow there are parts that are in the original in the original snippet. Yes. So what it does, it first it creates the variable for that goes after the semicolon. Next, in the same scope, it calls begin from this range, then it calls end, and then it does this the loop of that form with the iterator that comes from begin, and we have additional reference that we define here that takes the referenced iterator, and that's it. So we to implement that syntax, we need to implement the missing parts. Yes, let's do that, exactly that. So here first we want to have begin. Okay, let's have begin for cursors, and it will return something that we call iterator. For the end, we the same, we return something that is sentinel. It's just an empty struct in our case. So, and now the iterator that begins produce, it should have not equal method for the sentinel and plus plus and the reference. Well, let's do exactly that. Obviously, cursor the reference goes to get, next plus plus delegates to next, and not equal delegates to down. That's it. And now we have this now this syntax works for all templates that we that satisfies the concept.